In semiconductor production, doping intentionally introduces impurities into an extremely pure intrinsic semiconductor for the purpose of modulating its electrical properties. The impurities are dependent upon the type of semiconductor and the properties that it needs to have for its intended purpose. Lightly and moderately doped semiconductors are referred to as extrinsic semiconductors. A semiconductor doped to such high levels that it acts more like a conductor than a semiconductor is referred to as a degenerate semiconductor. In the context of phosphors and scintillators, doping is better known as activation. History. The effects of semiconductor doping were long known empirically in such devices as crystal radio detectors and selenium rectifiers. For instance, in 1885 and 1930 respectively, Shelford Bidwell and the German scientist Bernhard Gudden made the observation that the properties of semiconductors were due to the impurities contained within them. However, the process was formally first developed by John Robert Woodyard working at Sperry Gyroscope Company during World War II. The demands of his work on radar denied Woodyard the opportunity to pursue research on semiconductor doping. However, after the war ended, his patent proved the grounds of extensive litigation by Sperry Rand. Related work was performed at Bell Labs by Gordon K. Teal and Morgan Sparks. Carrier concentration. The quantity of dopant introduced to an intrinsic semiconductor determines its concentration and indirectly affects many of its electrical properties. The most important factor that doping directly affects is the material's charge carrier concentration. In an intrinsic semiconductor under thermal equilibrium, the concentration of electrons and holes is equivalent. That is, if we have a non-intrinsic semiconductor in thermal equilibrium, the relation becomes where N0 is the concentration of conducting electrons, P0 is the electron-hole concentration, and Ni is the material's intrinsic carrier concentration. Intrinsic carrier concentration varies between materials and is dependent on temperature. Silicon's Ni, for example, is roughly 1.08 times 1010 cm-3 at 300 kelvins, about room temperature. In general, an increase in doping concentration affords an increase in conductivity due to the higher concentration of carriers available for conduction. Often superscript plus and minus symbols are used to denote relative doping concentration in semiconductors. For example, N+ denotes an N-type semiconductor with a high, often degenerate, doping concentration. Similarly, P- would indicate a very lightly doped P-type material. Even degenerate levels of doping imply low concentrations of impurities with respect to the base semiconductor. In intrinsic crystalline silicon, there are approximately 5 times 1022 atoms per cc. Doping concentration for silicon semiconductors may range anywhere from 1013 cm-3 to 1018 cm-3. Doping concentration above about 1018 cm-3 is considered degenerate at room temperature. Degenerately doped silicon contains a proportion of impurity to silicon on the order of parts per thousand. This proportion may be reduced to parts per billion in very lightly doped silicon. Typical concentration values fall somewhere in this range and are tailored to produce the desired properties in the device that the semiconductor is intended for. Effect on band structure. Doping a semiconductor in a good crystal introduces allowed energy states within the band gap, but very close to the energy band that corresponds to the dopant type. In other words, electron donor impurities create states near the conduction band, while electron acceptor impurities create states near the valence band. The gap between these energy states and the nearest energy band is usually referred to as dopant site bonding energy, or Eb, and is relatively small. For example, the Eb for boron in silicon bulk is 0.045 electron volts, compared with silicon's band gap of about 1.12 electron volts. Because Eb is so small, room temperature is hot enough to thermally ionize practically all of the dopant atoms and create free charge carriers in their conduction or valence bands. Dopants also have the important effect of shifting the energy bands relative to the Fermi level. The energy band that corresponds with the dopant with the greatest concentration ends up closer to the Fermi level. Since the Fermi level must remain constant in a system in thermodynamic equilibrium, stacking layers of materials with different properties leads to many useful electrical properties induced by band bending, if the interfaces can be made cleanly enough. For example, the p-n junctions properties are due to the band bending that happens as a result of the necessity to line up the bands in contacting regions of p-type and n-type material. This effect is shown in a band diagram. The band diagram typically indicates the variation in the valence band and conduction band edges versus some spatial dimension, often denoted x. The Fermi level is also usually indicated in the diagram. Sometimes the intrinsic Fermi level A, which is the Fermi level in the absence of doping, is shown. These diagrams are useful in explaining the operation of many kinds of semiconductor devices. Relationship to carrier concentration for low levels of doping. The relevant energy states are populated sparsely by electrons or holes. This means it is possible to write simple expressions for the electron and hole carrier concentrations, by ignoring Pauli exclusion, where F is the Fermi level, EC is the minimum energy of the conduction band, and EV is the maximum energy of the valence band. These are related to the value of the intrinsic concentration via an expression which is independent of the doping level. Since EC, EV does not change with doping, the concentration factors NC and NV are given by where μ** and MH** are the density of states' effective masses of electrons and holes, respectively. Quantities that are roughly constant over temperature. Techniques of doping and synthesis. The synthesis of N-type semiconductors may involve the use of vapor phase epitaxy. In vapor phase epitaxy, a gas containing the negative dopant is passed over the substrate wafer. In the case of N-type gas doping, hydrogen sulfide is passed over the gallium arsenide, and sulfur is incorporated into the structure. This process is characterized by a constant concentration of sulfur on the surface. The reaction conditions typically range from 600 to 800 degrees Celsius for the N-doping with group 6 elements, and the time is typically 6 to 12 hours depending on the temperature. Process. Some dopants are added as the boule is grown, giving each wafer an almost uniform initial doping. To define circuit elements, selected areas, typically controlled by photolithography, are further doped by such processes as diffusion and ion implantation, the latter method being more popular in large production runs because of increased controllability. Small numbers of dopant atoms can change the ability of a semiconductor to conduct electricity. When on the order of 1 dopant atom is added per 100 million atoms, the doping is said to be low or light. When many more dopant atoms are added, on the order of 1 per 10,000 atoms, the doping is referred to as heavy or high. This is often shown as N+ for N-type doping or P+ for P-type doping. Dopant elements. Group 4 semiconductors. For the Group 4 semiconductors such as diamond, silicon, germanium, silicon carbide, and silicon germanium, the most common dopants are acceptors from Group 3 or donors from Group 5 elements. Boron, arsenic, phosphorus, and occasionally gallium are used to dope silicon. Boron is the P-type dopant, a choice for silicon integrated circuit production because it diffuses at a rate that makes junction depths easily controllable. Phosphorus is typically used for bulk doping of silicon wafers, while arsenic is used to diffuse junctions, because it diffuses more slowly than phosphorus and is thus more controllable. By doping pure silicon with group 5 elements such as phosphorus, extra valence electrons are added that become unbonded from individual atoms and allow the compound to be an electrically conductive N-type semiconductor. Doping with group 3 elements, which are missing the fourth valence electron, creates broken bonds in the silicon lattice that are free to move. The result is an electrically conductive p-type semiconductor. In this context, a group 5 element is said to behave as an electron donor, and a group 3 element as an acceptor. This is a key concept in the physics of a diode. A very heavily doped semiconductor behaves more like a good conductor and thus exhibits more linear positive thermal coefficient. Such effect is used for instance in sensistors. Lower dosage of doping is used in other types thermistors. Silicon dopants acceptors. P-type boron is a p-type dopant. Its diffusion rate allows easy control of junction depths. Common in CMOS technology. Can be added by diffusion of diborane gas. The only acceptor with sufficient solubility for efficient emitters in transistors and other applications requiring extremely high dopant concentrations. Diffuses about as fast as phosphorus. Aluminium, used for deep P diffusions. Not popular in VLSI and ULSI. Also a common unintentional impurity. Nitrogen is important for growing defect-free silicon crystal. Improves mechanical strength of the lattice. Increases bulk microdefect generation. Suppresses vacancy agglomeration. Gallium is a dopant used for long-wavelength infrared photoconduction silicon detectors in the 8 to 14 micrometers atmospheric window. Gallium-doped silicon is also promising for solar cells, due to its long minority carrier lifetime with no lifetime degradation. As such, it is gaining importance as a replacement of boron-doped substrates for solar cell applications. Indium is a dopant used for long-wavelength infrared photoconduction silicon detectors in the 3 to 5 micrometers atmospheric window. Donors. N-type phosphorus is a N-type dopant. It diffuses fast, so is usually used for bulk doping, or for well formation. Used in solar cells. Can be added by diffusion of phosphine gas. Bulk doping can be achieved by nuclear transmutation, by irradiation of pure silicon with neutrons in a nuclear reactor. Phosphorus also traps gold atoms, which otherwise quickly diffuse through silicon and act as recombination centers. Arsenic is a N-type dopant. Its slower diffusion allows using it for diffused junctions. Used for buried layers. Has similar atomic radius to silicon. High concentrations can be achieved. Its diffusivity is about 1/10 of phosphorus or boron, so is used where the dopant should stay in place during subsequent thermal processing. Useful for shallow diffusions where well-controlled abrupt boundary is desired. Preferred dopant in VLSI circuits. Preferred dopant in low resistivity ranges. Antimony is a N-type dopant. It has a small diffusion coefficient. Used for buried layers. Has diffusivity similar to arsenic. Is used as its alternative. Its diffusion is virtually purely substitutional, with no interstitials, so it is free of anomalous effects. For this superior property, it is sometimes used in VLSI instead of arsenic. Heavy doping with antimony is important for power devices. Heavily antimony-doped silicon has lower concentration of oxygen impurities. Minimal auto-doping effects make it suitable for epitaxial substrates. Bismuth is a promising dopant for long-wavelength infrared photoconduction silicon detectors. A viable N-type alternative to the P-type gallium-doped material. Lithium is used for doping silicon for radiation-hardened solar cells. The lithium presence anneals defects in the lattice produced by protons and neutrons. Lithium can be introduced to boron-doped P+ silicon, in amounts low enough to maintain the P character of the material, or in large enough amount to counterdope it to low resistivity N-type. Other germanium can be used for band gap engineering. Germanium layer also inhibits diffusion of boron during the annealing steps, allowing ultra-shallow P MOSFET junctions. Germanium bulk doping suppresses large void defects, increases internal gettering, and improves wafer mechanical strength. Silicon, germanium and xenon can be used as ion beams for pre-amorphization of silicon wafer surfaces. Formation of an amorphous layer beneath the surface allows forming ultra-shallow junctions for P-MOSFETs. Gold and platinum are used for minority carrier lifetime control. They are used in some infrared detection applications. Gold introduces a donor level 0.35 electron volts above the valence band and an acceptor level 0.54 electron volts below the conduction band. Platinum introduces a donor level also at 0.35 electron volts above the valence band, but its acceptor level is only 0.26 electron volts below conduction band, as the acceptor level in N-type silicon is shallower. The space charge generation rate is lower and therefore the leakage current is also lower than for gold doping. At high injection levels, platinum performs better for lifetime reduction. Reverse recovery of bipolar devices is more dependent on the low-level lifetime, and its reduction is better performed by gold. Gold provides a good trade-off between forward voltage drop and reverse recovery time for fast-switching bipolar devices, where charge stored in base and collector regions must be minimized. Conversely, in many power transistors a long minority carrier lifetime is required to achieve good gain, and the gold-platinum impurities must be kept low. Other semiconductors: gallium arsenide N-type, tellurium, sulfur, tin, silicon, germanium P-type, zinc, chromium, silicon, germanium, gallium phosphide N-type, tellurium, selenium, sulfur P-type, zinc, magnesium, tin, cadmium telluride N-type, indium, aluminium, chlorine P-type, phosphorus, lithium, sodium, cadmium sulfide N-type, gallium, iodine, fluorine P-type, lithium, sodium. Compensation. In most cases, many types of impurities will be present in the resultant doped semiconductor. If an equal number of donors and acceptors are present in the semiconductor, the extra core electrons provided by the former will be used to satisfy the broken bonds due to the latter, so that doping produces no free carriers of either type. This phenomenon is known as compensation, and occurs at the p-n junction in the vast majority of semiconductor devices. Partial compensation, where donors outnumber acceptors or vice versa, allows device makers to repeatedly reverse the type of a given portion of the material by applying successively higher doses of dopants, so-called counter-doping. Most modern semiconductors are made by successive selective counter-doping steps to create the necessary p- and n-type areas. Although compensation can be used to increase or decrease the number of donors or acceptors, the electron and hole mobility is always decreased by compensation because mobility is affected by the sum of the donor and acceptor ions. Doping in organic conductors. Conductive polymers can be doped by adding chemical reactants to oxidize, or sometimes reduce, the system so that electrons are pushed into the conducting orbitals within the already potentially conducting system. There are two primary methods of doping a conductive polymers, both of which use an oxidation-reduction process. Chemical doping involves exposing a polymer such as melanin, typically a thin film, to an oxidant such as iodine or bromine. Alternatively, the polymer can be exposed to a reductant. This method is far less common, and typically involves alkali metals. Electrochemical doping involves suspending a polymer-coated working electrode in an electrolyte solution in which the polymer is insoluble along with separate counter and reference electrodes. An electric potential difference is created between the electrodes that causes a charge and the appropriate counter ion from the electrolyte to enter. the polymer in the form of electron addition or removal. N-doping is much less common because the Earth's atmosphere is oxygen-rich, thus creating an oxidizing environment. An electron-rich, N-doped polymer will react immediately with elemental oxygen to de-dope the polymer. Thus, chemical N-doping must be performed in an environment of inert gas. Electrochemical N-doping is far more common in research, because it is easier to exclude oxygen from a solvent in a sealed flask. However, it is unlikely that N-doped conductive polymers are available commercially. Magnetic doping. Research on magnetic doping has shown that considerable alteration of certain properties such as specific heat may be affected by small concentrations of an impurity. For example, dopant impurities in semiconducting ferromagnetic alloys can generate different properties as first predicted by White, Hogan, Sewell and Nakamura. Single dopants in semiconductors. The sensitive dependence of a semiconductor's electronic, optical, and magnetic properties on dopants has provided an extensive range of tunable phenomena to explore and apply to devices. Recently it has become possible to move past the tunable properties of an ensemble of dopants and to identify the effects of a solitary dopant on commercial device performance as well as locally on the fundamental properties of a semiconductor. New applications have become available that require the discrete character of a single dopant, such as single-spin devices in the area of quantum information or single-dopant transistors. Dramatic advances in the past decade towards observing, controllably creating and manipulating single dopants, as well as their application in novel devices, have allowed opening the new field of Tronox. Neutron transmutation doping. Neutron transmutation doping is an unusual doping method for special applications. Most commonly, it is used to dope silicon N-type in high-power electronics. It is based on the conversion of the Si30 isotope into phosphorus atom by neutron absorption as follows. In practice, the silicon is typically placed near a nuclear reactor to receive the neutrons. As neutrons continue to pass through the silicon, more and more phosphorus atoms are produced by transmutation, and therefore the doping becomes more and more strongly N-type. NTD is a far less common doping method than diffusion or ion implantation, but it has the advantage of creating an extremely uniform dopant distribution.